RS-232, so that's what we're going to talk about today. We'll jump into it. I guess we'll save questions to the end. I'm not old enough to have used a teletype myself, so I'm going to kind of gloss through some of that. But all right, what is RS-232? What's it mean in the context here? So all of our favorite systems, the Tandy systems, Apple, Commodore 64, and the Commander X16, the NECs, they all had RS-232, and it was a way to let all of our computers talk to each other. And it kind of petered out around the early 2000s on the IBM PC. It had, an RS-232 port, but it's still used today, and I'll talk about some of the uses that it is used today. But that's what RS-232, that's what I'm talking about, and some of the history of it. And then I'm not talking about these guys. I'm aware of all these other ways to send information. So there is GPIB, which almost has, it was in the 1960s. It's almost as old as RS-232, but it is a parallel interface. Not talking about IEC on the Commodore, which is sort of a reduced version of the 488. I2C is still used today in a lot of microcontroller applications, but won't be covering that. It depends on a clock. Similar is RS-422 and 485. They kind of borrow a lot of stuff of RS-232. They're used more in corporate and industrial, but I'm not talking about that. But that you can get an adapter from RS-232 to that, and that's kind of what they look like. Yeah, and RS is not Radio Shack. Yeah, and I'm not talking about USB. All right, so kind of to kind of kick things off like an icebreaker, one of the earliest RS-232 games was actually this 3D game back in 1973. I haven't witnessed this myself, but there was a reunion in 2003, a 30-year reunion, and they confirmed that, yes, it used RS-232 to collaboratively play this game. So that's one of the oldest. There's older uses of RS-232s, but as far as games, that's one of the earliest ones that I was able to find. In 1982 is not well known, this combat game. It used RS-232. It wasn't a very good game. It really had no graphics. It was kind of like text with a lot of numbers. But the interesting thing about it had that idea is now an Apple Atari person, they could play the game with each other, Atari, Apple, and TRS-80. They could call each other and play the same game. And so at least that idea, I think, was groundbreaking, that you could use RS-232 to have different kinds of machines talking to each other. Just a laundry list of some others, but I wanted to highlight the Atari Comlinks. It's kind of the only game console that still used RS-232 as far as I was able to read. That Comlinks, you could do multiplayer. You could have like up to 18 people. So it's interesting how they do that. RS-232 wasn't really intended for that. It was really point to point. But I won't talk too much on the Atari, but just pointing that out, they were a user of RS-232. Then on the exhibit hall, I had Warcraft 1 playing RS-232, just kind of that idea of it's not networked. You have two machines talking to each other. All right, so this is the start of the real, what I'm going to cover, and I'll hopefully get about 10 minutes on each of these topics. Kind of the history going back to where this thing really started, talking about the Sage in the 50s, then some modern, where we started beyond modems, other things that we're using RS-232 for, and then some work that I've done recently, going past under 15.2, pretty reliable with RS-232. All right. So way back then, in the early 1800s, it was early kind of experiments. They were trying to figure out what material, what kind of metal to send these signals. And it's kind of funny, this is like the world's largest parallel cable, this guy in the early 1800s. It was literally, I think it was every letter of the alphabet. It had a ground and a power, so it's that times 2 wires. This guy, early 1800s, he had an 8-acre garden, so that must have been nice to have an 8-acre garden.
The world's first ribbon cable.
Yeah. So he's proven that concept that so he started, not sure if it's the same, so it's all battery driven. This is all before, they had electrical wires and outlets, right? So the voltaic pile was right there in 1800. And so I assume this guy is kind of charging it up so they can send their signals across a room. And so it built up from there. So that's the first idea of sending a signal across a wire. It was a little primitive because I think the first wire, like if you send an A, the signal goes off there, and it burned something that made a little smoke come up. So that's how you knew the A signal was coming across. So really primitive. But this is Napoleon Wars were just kind of ending around that time. And the Admiralty at that time didn't put more money in this technology. The Admiralty, they said, over in the UK, they had these semaphore towers. And they said that was good enough to send signals. Using telescopes, they could get 15 kilometers out of that and relay. So that was good enough as far as the military was concerned at that time. The shape of this was what letter. And so that was good enough for sending long distance communication then. But research continued up to Morse code. So we're all familiar with that for various movies. Some of the conventions on Morse code there in the 1830s, it had this kind of ratio. The dash dot, a dash was 3 times whatever a dot was, and then the spacing between them was 7 times whatever a dot was kind of the conventions. There wasn't a super standard on Morse code, even what frequency you would hear it at, but it was normally around, when in the movies you hear Morse code, it was around that frequency that you would hear. Samuel Morse, there's arguments on whether he invented the code itself. Kind of his innovation was, this register device that you could actually push a piece of wire to send that signal at a tempo without shocking the heck out of yourself. So good innovation there. All that telegraph technology was before the Transcontinental Railroad, so before the Civil War started. And then telegraphs played a major role in the Civil War. But that was 1861. Then what I read in San Francisco was like 2 days later, the Pony Express was disbanded after they had the telegraph wires across the nation. So talk about, technology putting people out of work. That was going on in the early 1800s. So the big thing was it's hard to build a machine to do Morse code because it's very duration. We could do it easily today, but back then they would have to build a mechanical machine and it would all be different for each letter. And so that was difficult. So next couple slides. Progress moves on to the early telephone networks. So there's this painting, John Gast, in the 1870s. She's carrying a spool of telegraph wire across the nation. Progress marching on. Of course, people have different opinions on that. But the idea that telegraphs was sending news bulletins, the post office was using it for telegrams. Sending weather reports was a good use of that information. And then, of course, the stock exchange. Those little teleprinters were coming around in the 1870s. But that evolved, of course, into the POTS, the plain old telephone service. So glossing over there in progress. The next was now this kind of innovation, going to the uniform duration instead of this varied duration was a big deal for the innovated progress there in the 1870s. So that word, Baudot, or baud, is the unit of how fast we send this information across. He didn't really come up with the idea of a 5-bit signal, although they will call it the Baudot code. This is kind of one variation that he came up with. The next slide will talk some features of this. But that was good for about 25 years using this baud through the telegraph system. On the next slide I'll show it was really a little clunky on how the Baudot system worked. But the main point I want to show, most of us with punch tape, it was really like a Murray code. How they arrange the A, it's like a different encoding. But if you really look at this Murray code, Murray, I think he was from New Zealand. It's arranged like the QWERTY keyboard. This is the top row of the keyboard, the middle row, and the bottom row. So his contribution kind of led toward the adoption of the standard QWERTY. There was a lot of competition around there. If things went differently, we wouldn't have QWERTY keyboards. It would have been a different style. But his main innovation was now just you have punch tape. You have holes on the paper tape instead of actually having to push the register to send signals across. I'm going to come back, I guess, to the innovations really in the 1920s in a couple slides, but that main idea that we had the 5-bit code. The other thing is they had figures and letters, so it kind of changed modes. You could send alphabet, but then you would send figures, and that would sort of switch the mode, and it would use the same bit arrangement, but now the receiver now knows now how you get numbers and exclamation and other letter symbols. Then if you want to go back to letters, you have to send another code. So it didn't really have upper and lower case. You have to kind of declare a certain mode. All right, so back to the Baudot. It was clunky because I had this cylinder thing, and each operator was assigned one quadrant of the cylinder. So one operator, he would manage his or her 5 bits, really, the 5 keys, and that was really the input that they would They would have this little keyboard. The way the signal was transmitted was a different order than you typed it. So again, I haven't seen one of these in operation, but my understanding is the operator would push a key, say they want to send to A, whatever that is, and the keys would stay stuck down until this rotation came back around. Then it would do his 5, whatever the keys were, do the transmission order of that. And then they would have this little cadence signal, which I don't know if it was a light or an audible tone. I think they would hear something that, and then all the keys would get released. And then they do it again for that duration. So I would have multiple people, each one assigned around that, and that's how they would send their message out. So again, it was innovated for the time, but it was kind of clunky for us to think that you would have multiple people in sync with each other at this tempo to send out a signal. All right.
Each operator sending a different message?
So yes, it was a different message, but just for the tempo-wise, each one would have their own part of the cylinder, the round portion. So the next operator would have this one, and yeah, it would be connected to a different receiver. What was that?
So it took like 5 people.
Yeah, there were different configurations. Some of them were 4. This particular one was 5. And yeah, so imagine you have a news bulletin and you need to broadcast it to 5 newspaper groups, right? Well, each person has to do that. Like he'll say, okay, it's the same message, but it's going to newspaper A, B, and C. But it was multiplex in that they could each do it simultaneously through the rotation of that. Now, but they had to train with each other, and synchronization was obviously a problem. They all had to be really in tempo with each other, or you get garbled letters. And all right, so I know this is a wall of text. The innovation was the start-stop system. So if you know RS-232, it's involved or related to the start-stop, the framing of data that's going across there. But that idea, that's what I was really looking for, is when did the first start and stop bit, where did that word and idea? And this is the earliest. This is in a book, Printing Telegraphy. The era begins. He's writing kind of his memoirs in 1967, and he says right around 1909, kind of that first idea, and I'll have a picture on the next slide. But the synchronization, the story is like those early stock tickers. They would have young boys run out through the city and resynchronize several times a day, and so that was very tedious to resynchronize because they would drift out from each other. So it wasn't as glorious as it shows in the movies that you would get your stock ticker or whatever your information was. It would just stop working at some point, and so someone has to resynchronize its clock if there was a power glitch or something happened. But the wording, they had that idea, what they call finding the letter, which is kind of funny because we can do that today with when you're setting the baud rates. You're kind of, well, what baud rate is this other system at? I have to guess until I start seeing letters coming across. So that was a term that they used there in the early 1900s, finding the letter. So that 1909, that Klum was one of their engineers, and he said, well, you can have this start and stop signal around this cylinder as your signal is coming across. And I think the next slide will show, they didn't literally stamp the words start and stop on there. I'll bounce. This is kind of what they look like. The stop bit was always kind of longer than your data bits. So even today, if you're familiar with stop bits, you have that choice. They can use 2 stop bits, 1.5 or 1 stop bit. Modern systems, it's almost always 1 stop bit. But it's literally this metal piece is longer than all the other pieces. This one is an 8-bit wheel. This isn't the part that spins. It had like a sweep, a brush that hit these as they went around. You watch videos with Curious Mark. He's done a tear down and remake of some of these old teletype machines. So he had those pictures. It was another famous book with the Telewriter Fundamentals that described how these cylinders work. It was like the diameter of the receiver had to be a little bit smaller because it had to run faster. Over in Europe, different power settings, it might have different speeds on these things. So you kind of get, it'll vary a little bit whether it's 45 words a minute. The key is, going back to Morse code, the best operators that could do is about 50 words a minute. So that was sort of the level to beat. So you could build a machine that could beat a manual operator at 50 words a minute. And this is where they finally started having machines that could outperform most, even the well-trained humans. I think in the 1930s, it was like the world record of the Morse code. He was able to do 50 words a minute. But that's a very experienced and well-trained operator. I don't know what caffeine he was on. So, because you see the videos of them just clicking away. It's So again, referring to this book, again, he's honoring this guy, Howard Kroom is credited coming up with that idea of adding a stop bit. And to really kind of summarize it, the idea was it was really synchronous before, where you had and as soon as they fell out of sync, the communication fell apart. He's saying it definitely took a mind not bound or hampered by standard and accepted ways. Like somebody thinking outside the box is not the normal way of doing things. And basically he summarizes it as the simple idea of having the transmitter start the receiver through the start and stop bit instead of having them both start at the same time. Later on, a lot of people, synchronous is faster if everyone has the same clock and you know what information you're exchanging. But as soon as you start typing something, people type at different speeds, or they have to think about what they're about to type or communicate. So you don't want to have just the printer just printing nothing. You need it to stop for a little bit and wait for whatever data is coming across. So innovative idea on the early teletypes. Okay, so like I said, this is supposed to be about RS-232, and I haven't really mentioned RS-232, so I'm building up to it. So we had, I'll go by these pictures. We had Morse code where you kind of hear the dots and dashes and people would write it down. Then they had teleprinters that could print out the dot and dashes. During the Civil War, they revised the old Roman decoder thing, so now you have to someone write it down, second step, decode it. 1920s, they finally get punch cards and whatever the information was. Like say it's the weather and you want to record, the average weather for the last month. You could record that data onto a punch card. Then they start building machines that could sort all that information. And then finally you can build the teletype where no one really has to write that information out. You kind of punch it here and automatically send it to another area. So that's 100 years of evolution of just kind of figuring out those aspects. Where if you just had some RAM to store that information, so that was really the next kind of evolution is drum memory. Whatever data you're receiving, you have to store it somewhere. Implicitly, it could be stored right on the punch card. That literally could be your memory. But they want to get it a little more faster and efficient, so they needed some way to have memory. All right, so now the Sage machine. Whirlwind is kind of one of the first big government projects of a computer, but right, 1952, there was urgency of the Soviets had recently done their hydrogen bomb, so they wanted to kind of look for any air interceptors. So they said, we're going to throw a lot of money of how we're going to build a networked, across the nation, a system to do all this detection. So IBM was the prime on that. They built the 704, and that kind of made IBM what it is today, at least in my opinion. Right? They were just kind of a typewriter company before, and then this turned them into a computer company or a technology company. These are the other people that were involved with that: Rand, Burroughs, Western Electric, Bell Labs for sure. And all right, so the picture is funny, right? It's a little heart tattoo on what kind of. Yes, but it's showing the innovation of, this is the late 1950s. They had those light pens. IBM didn't develop core memory. It's known that they obtained a patent from Wang in 1956, and they paid like $500,000 for it even then. So a lot of bit of money to get that patent. But they incorporated core memory, the idea of tape storage, and not audio tape, the 7-track or early versions that they called that. 4chan was developed on this platform. And the idea of not really using typewriters anymore, but keyboard terminals, multi-users and real-time response, so not really a batch processing where you batch it into a sorter and wait for your punch cards to come back. The idea of PC board construction came about on this system. I think an Australian was started in that material, the multi-layer PCB construction. But for us here today, it's this thing. How do you get this computer? You have radars out here, and they need to feed information to a central computer and triangulate where these things are coming from or communicate where they're going to be in a few hours. So that's what the Sage system was built for. Some people say it was obsolete almost. It's one of those, it was obsolete almost as by the time it came online. We've heard that story many times. Because in the 50s and 60s, it was like planes weren't, it was tuned to really search for large airplanes, but the big concern then was, of course, ICBMs coming at higher altitudes. But it had a long life. It was upgraded over time and was put to good use. So all that computer technology evolved from that early stages, starting in 1952. So computer-to-computer communication, what was their solution for that? So this is sort of the first modem. They built, the Bell was one of the contributors on that Sage system. So they built the dataset 101. The dataset, my understanding, was a set of cards, and it basically how you configure basically its equivalent of a baud rate and what kind of protocol it was talking about. So you had little cards that you would put in here. I found the manual. So someone through, I thought I had it on here, CC Talk, found the manual, the 1959 of the dataset. And one kind of key point I got out of that manual is it used a double stop bit. And I thought that's interesting. So they're calling out, even then, using that terminology of 11 bits, operating at 110 bits a second was their transmission speed. And these are different networks at the time, for lack of a better word. That's what the Sage system used. That's sort of the military spec. I don't think that was sold really to businesses. It was a couple years later, Bell was kind of, they said, all right, we'll make a consumer version of this modem. And so you start to see, if you're familiar at all with RS-232, you start to see what kind of looks like RS-232 as far as the pin arrangements. You got the ring indicator, the DSR, data terminal reader. The only difference is they don't have RTS yet, the ready. Yeah, just RTS, and then they have some power lines on the pins. And that's the phone line companies at the time. I'm not sure what they used the 20 volts for, but in that manual, 1963, it calls out 20 volts on those pins. So it's almost but it's not formally called RS-232 yet. So one thing I've noticed in all these vintage computers, I used to think, what's the oldest thing that we have in common with our ancestors of computers? And I used to think it was the power cable. But you look at this is its power cable. It's actually a round kind of thing, right? Like power cables hasn't changed in decades. Well, actually, the oldest thing we have in common with it is that DB25 interface, that Canon came. This original modem, it was using that interface. Canon, they were still making printers even in the 50s. And so that DB25, which I'm going to highlight in a couple slides here, it was on that interface on the first modem. But the power outlet that we use every day to plug in, our power things are getting smaller, right? For monitors, we might have little smaller, or especially even USB now giving us power. All right. DB, you might see it's a D sub-miniature, so it's really a miniature version of a larger IBM cable that they had. Okay. So another thing in the 1963 modem, if you're not familiar with modem, how it relates to RS-232, the computer will talk to the modem and basically it sends the signal or converts the signal into an audible tone, and these are the frequency they picked. So another aspect of the data set, like you can put in different cards and it kind of configures what frequency that they communicated on for those other three networks that it was supporting. So at the time, it supported 300 baud, and that was, even then it was considered slow. But 300 baud, through the quality of the phone lines and copper lines they had at the time, 300 baud was like the reasonable fastest rate that they had. It was compatible across the power units here in the US and over in Europe. So that's why we ended up with 300 baud. And like I was saying earlier, the best trained operator, they could do like 50 baud. So this is orders of magnitude faster than that. No human's going to be able to compete. Even touch typists, they're going to have trouble. They can get close to 300 baud probably. Okay, so RS-232, the actual spec is, I was not able to find, so last year I've been trying to dig around the original spec, which was claimed to be May 1960, and I cannot find it anywhere. So I don't know if that's really true, that it came out in 1960. But 1963, I don't have hard copies of them, but you can go to the TAA. TAA is now the organization that manages or owns the standard. You go to their website and you can actually, they charge a lot for it, like $180. So I wasn't that interested. But they have these dates on their website. So I'm going to take their word for it that if somebody wanted to spend $180, close to $200 to get the original A and B standards from 63 and 65, you could obtain them. So most is the EIA version of it. EIA was the previous organization that held the standard, but most of us can get our hands on the 1969 version of that standard. And almost all RS-232 today, they'll probably call out that they comply with RS-232C. So like I was showing on that diagram earlier, what was different between A, B, and C. I'm not going to go really all through all of them, but like that power, the 20 volts, that's not there on the C version. Down here, so RS-232 actually doesn't care how you encode it. It's your choice whether it's going to be how you interpret the signals that you're sending. RS-232 doesn't really dictate that you have to use a start and stop bit. In the notes, I have the website that calls these out, and you can kind of read through the standard. And it also doesn't really control the order, the big Indian, little Indian kind of thing. All right, so we're going to dig in a little bit more. So since I didn't want to buy those old RS-230 manuals, I looked at the datasets manual from 1967. And you see that vocabulary where it's calling out the pins. Really the thing about RS-232 is the voltage levels and what pins are used for what. That's really the essence of RS-232. Even in the 1967 dataset modem manual, the manual was dated 1967, but I believe it's from about 63 or 64 on what product it's representing, the 103A modem. So it's these pins. It's not using all these later standards. These are secondary pins. We'll talk about those in a little bit. But you're starting to get closer. You see commonality with modern interpretation of RS-232C. The big difference, they got rid of this protective ground. When I say got rid of, it's still there on the 25-pin version, but I mean on the 9-pin version. One of the pins that they dropped, the protective ground, and they added the RTS signal. Okay. Next. So yeah, most of us play with the smaller version of the RS-232, only the 9-pin version. We don't really need, that confuses us with a parallel cable. This calls out the secondary transmissions. There was like a sub-channel where you could potentially get a little more efficient transmission using those, and 2 pins were unassigned. So kind of dealer's choice on what you use those pins for. So that's RS-232 established as a standard in 1969. Like I said, they got rid of the protective ground. It's now the request to send pin. This smaller version, at least in my view, became really popular starting when the IBM, not the original PC in 1981, but later in 1984, the AT kind of really everywhere, everyone used a 9-pin serial port. Now I'm going to talk about Atari in a little bit, but that standard, the actual so IBM came out with that serial card that used the 9-pin, but that standard wasn't really written down until 1990. And I've noticed that with a lot of standards. It's like 5 years later they finally write it down. So, the standard RS-232 doesn't really call out that you have to use a DB25. All it really says is you have to use a 25-pin connector with 1 row of 13 and 12, so that strongly implies you're going to use the existing DB25. I've noticed a lot of motherboards, like the 386, 486 era, they'll have like this 26-pin, or even the X16 actually has a 26-pin. No idea what the 26-pin is used for. It's not part of the standard, so it's really technically a non-standard interpretation of RS-232. Spec-wise, it's only supposed to work for 50 feet at, I think, 9600. And then you can go longer, but then it just degrades the signal, and you can have slower baud rates, longer distance than that. It's saying basically these are the pin assignments that you can't use them unless they're marked as unassigned. Yeah, especially as unassigned. Okay. I was reading through a 1991 version of this spec, and it looks like they made a little typo. They had this secondary clear to send repeated twice, but pin 25 is just unassigned. So I thought that was funny, whoever made that mistake in the 1991 version. So that's kind of reasons why they've evolved past the C. They make little refinements. They might update the table. Like this table, the European equivalent of this pin assignment. All right, more particulars. All this is saying it basically don't go over 25 volts, but it's stay within the 5 and 15 volts. So it's the standards establishing those constraints. That's all I'll cover on this one. Just, we've got a lot of other things to cover. Okay, so I was like, okay, what was the earliest where RS-232, the word, was used in publication? Like I couldn't find that 1960 manual. I was really kind of trying to reach when did the word RS-232 really start? So I manually searched through all the old articles of Datamation. That's a popular magazine that went through decades, maybe, I forget if they made it to the 80s and 90s, but maybe about 50 years. Anyway, this is what I found. November 1966 is the earliest that I could find the word RS2 was in publication. So not like a military spec or some internal to some company. This is out in general audience publication. So General Electric was actually making a modem. I mean, they didn't call it a modem, they called it a data set. And it was 1800 baud modem. What year? In 1966, and you can get up to 2400 baud, and it may be hard to read, but it's close to $2,000 for 2400 baud modem back then. But it says it's compatible with RS-232. Now it doesn't say A, B, or C. This predates the C spec. So somebody found one of these. It probably wouldn't work with the modern day, the C standard. So that's what I found, 1966. If anyone finds earlier than that, let me know. Now 1970 in Datamation, It calls out faster modems by this company called Datamax. I've not been able to find any one of these. I don't know if that company exists or what else they made, but they're offering 4,800 bauds and 2,400 baud modems. Yeah, prices aren't on here, but out of Michigan, yeah, they say better modems are built. But that kind of speed, at least the commercial level where you're just sending high-speed data between computers. This was an early modem that was available. Now we're all probably pretty familiar with the Hayes modems. You know, we know him. He built the early S100 board, early modem. That's kind of his claim to fame. It was a 300 baud modem. A couple highlights here. You know, you can get the parts for $50 if you want to pay someone to do it. It's close to $300. It still supported TWX. Probably some people still have versions of this modem. It didn't have the Hayes standard, so a lot of us are, that came a few years later in the smart modem where it had kind of starting to standardize how you talk to a modem over the RS-232 port. AT being common, get the modem's attention that it echoes back okay. But I thought it was interesting this Datamax, and so if anyone knows more of the history, modems were available as early as like May 1970, higher speed modems, higher than 300 baud. Okay, good. This is my halfway point. I think we made it. I think we're about halfway. So this is my little intervention. There was a little bit of drama about ASCII between IBM and everyone else. IBM liked the idea of standardizing how we should communicate, you know, the letter A, but they had one little issue with PL1. IBM had already developed EBDICT, but they had developed PL as like programming language 1, 1963. Then PDP, they had a 6-bit, and Radix 50 were some other alternatives. In this presentation, I don't really touch a lot on the 6-bit era. It was very brief. But their main opposition is they really wanted the vertical bar to be a solid vertical bar. It was really the crux of why they didn't really want to adopt ASCII. There were some, I don't want to say emails, but letters and discussions back then. So they made a compromise like, okay, we'll put a little dash in it to distinguish it from whatever the OR operator looked like in PL1. So they had a legitimate concern about it. If it was just a regular vertical bar, it wouldn't be quite the same vertical bar as whatever OR operator meant in PL1. It's funny, though, that whatever happened, like a decade later, ASCII revised and made it a solid bar anyway. But you see on the old IBM cards, it's got a little keyboards. It has a slit in it. But that's not true ASCII if you put a slit in it. Depends on what you're talking about. There are a few other little debates, but that explains why it took so long for ASCII. ASCII is around the same time, 1963, when the first versions of it, but it wasn't universally accepted. Why it still took about 15 years before everyone's got on the same page and start using ASCII as an international standard. Okay, so now we'll get back to more fun parts on what RS-230 is used for. So these are the common things. We're all familiar to use for mice and trackballs. I had out in the exhibit a drawing tablet. This one pulls power, so that kind of violates the RS-232 standard. You're not really supposed to do that over RS-232. This thing, one of the pins on RS-230 is like the ring indicator, for example. If you don't have a ringer, you could use that pin for something else, or at least that's what they're trying to draw a current through the other pins, which is a little cheating of the standard. And then printers, there were some serial port printers. So those are common things. Now I'll go through some unusual things. RS-232, check out point of sale machines and scanners that we were using RS-232. The VT, the early terminal here, actually, they don't call it RS-232, they call it EIA, which was the organization that maintained the RS-232 standard. So you'll search it and you won't see the word RS-232 in there. And they had a choice. They could use the old current loop. They had two little cards, so the next page, graphically what it looks like. If anyone's got a VT52, you can see what kind of interface card it has on the bottom plate here. And you can swap in either current loop 1, which is more compatible with the old teletypes, or they call it EIA, which is an RS-232 one. Let me go back, make sure I didn't. These are the pinouts that it's using, which you'll see comes in line with regular RS-232. Although it says 25 volts, you know, they go way to the high end because that's what it supported. I think there's little jumpers on one end to set whatever the baud rate is. I'm not sure where those are. I think it's these things, actually. You dial these to get the baud rate. But there's UART thing. So RS-232 and UART, and why do we need a UART, and what is a UART? Earlier on, I had the distributor that had the start and stop, and I don't think I highlighted back then, but it was like, it's a mechanical UART. And so what is a UART? What is that? I'll talk a little bit more later, but it's a component that adds that start and stop bit that does the framing for you, so the CPU or the processor doesn't have to do it for you. It also has a little bit of buffer if something's running a little bit faster than you or you get interrupted. It can handle that also. And it also handles the baud rate, right? It has a tempo. So depending on the baud rate in the machine, if you're sending something at 2400 baud, that could be super fast for your machine, or it could be super slow if you've got a very capable machine. You don't want to waste your CPU kind of looking at the clock. Is it time to send out the next bit? You could be doing a lot of other things during that. So those are the things that a UART does for you. So it's interesting, the VT52 is one of the early UARTs that I've seen. There's a 1971 from, I think, Texas Instruments also. I had that out on the display. All right, sticking through the fun things. I was watching Ghostbusters, and I saw this machine here. It's not a prop. It was a real machine back there, the electrolyte analyzer. And so I said, hey, I wonder if it used RS-232. And I looked up versions of that model, and it did. Serial port right there on the back. So that's fun. And plotters and this it's not a photometer, if I'm saying that right. Both of those used RS, so scientific equipment, both using RS-232 called out there. I think the plotters, they're in the main hall today. He had them going this year. More scientific equipment, this ocean spectrometer. Expensive, and that's, in the last 5 years, last few, I don't know the exact year on that, but they're still making that and still uses RS-232 there on the back. Well, I'll skip on this next one. I found up this government study in Mississippi, 1989. They're using RS-232. And the government's thorough, right, to a fault. They had to do this long proposal, right, on what all the equipment they were going to use before they started doing that. They're using like one of the little Tandy Model 100s. This is like a water level sensor. So imagine it bobs in the water as the water level is coming up and down. I don't know exactly what, not like ocean water, I forget what they were using, but it's like a 20-page proposal on how they're going to do it. It talks about down to what pins they're going to use and what vendors are going to use. It also has this little cartridge reader, and I hadn't noticed that. I did see one on eBay. It does exist. It's not like a compact flash, not SD card, but 1989. I don't know what kind of cartridge reader it has. It's not a tape. It is an actual cartridge, so they spent some money on that. But that was RS-232. I'd like to find one of those and play with that one of these days. So used by government projects that they're using RS-232. That's my Commander X60. I had that out in the exhibit hall. You still use that. You can, anything that can speak RS-232, you can connect it up to these high dollar servers. I have one of these, the DL580s. It's like a 60-core server right on the back end. If you want to set up MAC addresses and IP addresses of network card, right? If you want to do some kind of basic maintenance of the hardware setup, that's something RS-232 is still used today for. At the previous VCF in SoCal, and I saw this. There was actually a hand scanner that used RS-232. I'd never seen that before, and I made the guy like open it up, like prove it, and I saw the RS-232 port on the back, so that was fun. The Palms at the late 1990s to upload data and resynchronize at the end of the day, they used RS-232. These PTZ was at pan, tilt, zoom. They're still using RS-232, and I'll have a picture on that coming up. The keyboard on the K-Pro actually used RS-232. The pin out here is a little funny, but it was a 300 baud communication, and I guess you could have a 50-foot cable if it's regular RS-232. A lot of paper tape punches will still use RS-232. All right, here's that. When you go to those shows that have the laser lights and sounds, right, they're probably using RS-232 in some capacity where something happens and they want to trigger some information. And I tried to verify that. I looked up the manual of this thing. I was like, how do I use RS-232? And it had like a little protocol, a little plain text thing where you establish your baud rate, and now you're commanding, I want this light to come on at this time. And it's easy for an operator that's like plain text. I don't have to learn how the bus of this system kind of works. I have a little language here. G1 is some other light sound. I can adjust the volume of it or the color that I want it to do and for how long, maybe a duration. So I said, well, that's cool. And then CR is just carriage return at the end of whatever you want to command. So they script it up, whatever they want to play for their show, or in real time, maybe they can mix things up. All right. A lot of people might know I was using this out this week. I was playing a video on the X16. but I wanted to cycle through several videos. Well, I found this thing to help me do that. The software we had didn't reboot at the end of the video, so I don't want to stand there and reboot all the time. So I said we can automate that. It's RS2, it's a PS2. You can basically automate what you want the key, and they're usually for automated testing. You write these little scripts, and I want the keyboard to type this, and so you communicate it through RS232, and you can set the tempo, how fast you want to type. You can do special Control-Alt-Delete and other shift keys and modifiers. So that's an interesting use of RS232. That I was using the reboot computer. You know, I set it like every 5 minutes to set it reboot. It's not cheap. It's a couple $100 or something like that, just because he probably doesn't sell a whole lot of them. But telescopes still use RS232. So I do astronomy work also and can verify this. Meade and Celestron have their own little protocols, and I wanted to verify, is that true? So the source code to Stellarium is out there, and you can look at its RS232 module and sort of, the next slide I think shows more of that. But that idea of using a telescope was clear back with the Poly 88 when it came out in 1976. This was like their early advertisement. And it's hard to read on its screen or something, but it has the right ascension and the alt kind of address of whatever star it's supposed to be tracking, and you can actively track whatever you're trying to center the telescope on using RS232. Data exchange using all the protocols, and it's the history of kind of the file transfer protocols. I'll talk more about that at the end. But back on that telescope stuff, this is the language I use. It's a plain text. I want to go to this 34 right ascension, put in the numbers and resolution and where I want it to track, and command the telescope. I'm going to go back. Like the K-Pro, I guess it's not on this one, they do use like a 4-pin interface, but they don't need control flow. It's not that fast actually on a telescope. It doesn't just slew that fast. So the regular hand control itself is 9600 baud. They still don't need any flow control on that, but the auxiliary port is faster, and they do need some control flow on that. All that was like perfected as far as consumers could buy that at the end of the 1999 telescopes today. A lot more of them are using USB, but that same language is supported on how you control the telescopes. Okay, the Atari. Even though it looks like a 9-pin port, it's not always RS232. For whatever reason, Atari, they used, this was 1977, so they did it ahead of IBM. This is the Atari 26 on the back side. It looks like a regular 9-pin thing, but it's not RS232. You can read the pinouts, the power, and how you hit the different buttons. This koala pad, I've only seen joystick versions of this, but I saw on the back of the box somewhere that it claimed it had an RS2 version of it, but I haven't actually seen one yet. But to say, just because it looks like a 9-pin thing doesn't mean it's always RS232. So just also, yeah. Oh, for the koala board, okay, or the koala pad, yeah. All right. Well, there's joystick versions of it, and I don't think either one of them work pretty good. I don't know. I tried one. The one I had didn't work very good, but yeah. So this was fun. I saw this on YouTube. This guy said he got a PBX board and he fired up a modem, and he just using his laptop, he recorded the audio, and he could prove the serial analyzer of how that modem was sending out its signal. And it had enough resolution, you could zoom in on that, and if you don't know what an H looks like in regular ASCII, trust me, it's that arrangement. The video that he had was a finer, and you could zoom on it a little closer. But you're sending out an H, and then what happens after that? The receiver has to actually send that H. So at this point, it's sent the H out. But now the sender has sent the H out, and now the receiver has to react to it. Mostly in a terminal, all it's going to do is just show it up on the screen. But you could also buffer it to a file, send it to a printer. It could be a command to move a character if you're playing a game or something like that. So that takes time. And here you're just typing. So to us as humans, right, 30 milliseconds is the standard kind of average of how much delay you have between key presses. So when you're typing the word hello, you usually have 30 milliseconds. And that's a lot of time. A computer can do a lot of cycles in there. But there's a limit. If you have an old 1 megahertz computer, you can overdo it. And that's why old computers have to talk at the slower baud rates. They only had like a 1 byte buffer. There's only so much they could do. And a stressing thing for those old computers was just scrolling the screen. Now different computers there were some exceptions to that. Some had some hardware assisted scrolling. But when you're testing kind of is my baud rate working on this old computer? Make sure you go clear to the end of the line, clear to the end of the screen, and make sure it's scrolling and you're not losing any characters. If you get an interrupt and you have to scroll the entire screen, and then you might start dropping characters then. But that's a neat little window that just listening to the audio out of a modem, you can see the signal going back 100 years earlier, that they were drawing those Murphy charts showing the mark and space arrangement of sending out these letters. All right, so why do we need a UART? I kind of covered it where it handles that task of attaching or framing the transmission going out with the start and stop bit, and then removing them when it receives. So you have one little chip that's hardware accelerated doing all of that work for you. It does the pacing of whatever the baud rate is, so while the CPU can do other stuff, it doesn't have to do it itself. It kind of helps a throttle, as all the UARTs will have some amount of buffer. So if you have a slow computer talking to a fast computer, it can help buffer some of that. I've seen where you've had some computers are so slow, it gets the signal to stop, but it can't stop fast enough. It kind of has a momentum of that information. So I've learned sometimes that's why you might want to turn those FIFO. Don't use the full capacity of the 16 bytes. You might move it down to 14 or 8. You might start at 8, start at half, and see if that works, and go from there. But then as microcomputers got more capable and started becoming more multitasking, the UART became more essential. To kind of that buffering of, I've got another program that's sending information off this serial port, and I want to do other things at the same time. So there's a term out there called bit banging, where if you don't have a UART, you can kind of do it yourself in the CPU. And this is a pretty busy diagram, but it's kind of showing, yes, the CPU could do it on its own, but that's why bit banging is always less efficient than having a UART do it. Most of the CPUs are going to work in whole chunks of 8 bits. The UART isn't limited to that. It's going to work 1 bit at a time. So you're going to kind of waste. If you need to send your H out and you're only framing it with 3 bits, you only need to send out 11 bits, but it's going to send out a full 16 bits. So that's kind of wasted time when you're bit banging it. The other thing, you might have a parity bit in here that needs to interject. I haven't really talked about the parity bit, but it says how many ones and zeros that you have in there. So it's just I don't know, poor man's CRC, I guess. Down here, yeah, that song, Missy Elliott, you gotta flip it and reverse it. That always gets in my head when I'm talking about bit banging. You have to reverse the order that's going out and flip the bits. So there's that concept of bit banging. You could a CPU on its own. It's not really the CPU really doing it on its own. It's always almost having a VA or PA chip to kind of help it at least push those bits out. But the CPU is doing the work of the framing and the ordering of the bits coming out. So it's usually assisted bit banging is what I would call it. I found a program online called Serial Tool, which is pretty cool. And you can kind of type whatever plain text you want, and it'll visualize what the signal should look like across RS-232. I don't think it's a web-based app, so you kind of have to download it and run it, but it has this byte visualizer feature. So that was pretty neat. So if somebody wants to visualize what RS-232 should look like, and it has little buttons where you can add in parity bits and your number of stop bits. This is what old UARTs look like. This was an early, can't remember his name, the PDB-1. He wanted to hook up his teletype to the PDB-1. So he's that idea of building an early UART. Finally got that done. Then formally, one of the earliest UARTs, a lot of us think about the 8250 on the IBM PC, but really a decade earlier was this 1402, I believe from Texas Instruments. No, what's TR?
Pretty sure that we'll kind of this in the ADM3A.
Yeah. All right. And then around when the PS2 came out, this faster 16-byte buffer came out and became popular, the 16550. So that's kind of the history of UARTs that are available out there. The standard one was clocked at 1.84. I found another UART. It was for the S100. It was half of that. It was 0.9 clock rate. So that was interesting. Now in the late 80s, this chip came out, and that really helped. That's probably a large reason why we have RS-232 still, is because it came so darn cheap for any system. Just toss RS-232 on anything. For pennies, they could add RS-232 to any system. And so since it was so affordable, early days of USB, there was some licensing and issues, so it was kind of expensive. But again, we're not talking about USB and other things.
There for $6.
Yeah, yeah. So it was just cheap and easy. This chip, what did they call it? The Max 232 IC. If you didn't have to do that, then you have to have all these other components and do the level shifting yourself. In the color computer, this is literally in their manual from 1980. One thing is they only went to 12 volts, and I thought that was kind of interesting. The spec was supposed to be 15 volts. That probably just limits the distance that you could run a line on that, but they've got these little level shifter components. But you can still get these chips. They're still available today. Yeah, Texas Instruments had a different version number of that. Oh, but in this article, he really... he disses RS-232. He says, who in their right mind would choose to have a 12-volt interface, expensive connectors, a limited distance, dare prone? You can't network. You can't have, it's just point-to-point. In 28 years, we're still using it. It really comes down to cost, just to have this chip that's available for a few cents. But that's 1988. Kind of the need for RS-232 is starting to kind of go down even then. So this is how really the UARTs work, where they have to run faster the sample, the incoming signal. It's usually 6 times faster. I have seen cases where it's only 8x or 32x. I don't know what drives the decision there, but in most of them, it comes when you're writing software to really take advantage of UARTs. You kind of need to know those clock rates to set up your baud rate, to set up the dividers. But really, it's running faster, just like the old teletypes, where that receiver distributor had to run faster because it's waiting for that start bit to happen. And that's its job in life, is waiting for that start bit. It tries to land somewhere in the middle, and it does like a best 2 out of 3 hits, is what this is showing. So this is the 16x kind of clock rate. So again, in a nutshell, you have a chip here that's doing this signal analysis really right in real time. We have 3 gigahertz CPUs. They could do this, but as soon as you have an interrupt, right, you really need to focus on this problem. So interrupts will mess it all up.
Radio Shack on the color computer, the video text cartridge.
Yeah.
Use the horizontal video interrupt. 25x.
I remember hearing about that. Yeah, I forgot about that. Okay, yeah. We're in Tandy Central, so we have our experts about. Okay, so this is a neat picture. The penny whistle modem, Lee's here this year, so that's, if anyone has one, get it signed by Lee while he's here. He's the inventor of that in 1973. But if you wanted to visualize how modems, the secret really is they were still, from my understanding, is they were still 600 or 2400 bauds, but they had these, how they embedded the audio signal was they spread the signal across, and now we have computers capable and we can see that signal in real time. So this is another person on YouTube where you can see the modem signal right in real time. And modems, they kind of capped out right around 57.6. There technically was a slightly faster. It's funny because it was called v.last. They thought it was going to be the last protocol. It was v.fast and v.last. They could do download at 57.6 and upload at 33.6. There was a slight revision, v.92. It didn't really dramatically change it, but they increased really the upload rate. So it's really the last kind of big standard on modems. But as the data is coming across, that's how they modulate it across multiple frequencies, where they're sending more data. I don't want to say per bit, but I guess per transmission cycle. It's fundamentally how, and they have the fancy words for the different protocols that they support. My only expertise on RS-232 is that I ran a BBS in the 90s, so I don't. Most of us are familiar with RS-232 in that regard. So I'm just a consumer of it. But now I'm realizing, yeah, it was used for a lot more things than just modems. So speaking of that, where with just modems, you have to have, if your color computer doesn't have a built-in UART, okay, you have to add one. And through the expansion cartridge, it had the serial I/O card that on board it had a serial I/O, but it was have some videos about it where I've tried to use it, and yeah, it was really limited to 1200 baud. This thing can get you up to 9600 baud reliably, but it's talking at bus speed, even though it's a cartridge going in there, basically bus speed. Then through RS-232, it connects to whatever modem you want to use, and you would generally use a Tandy modem if you're using a Tandy system. You didn't have to use their brand modem, but most people with the Tandy systems, they did, just for the price reasons. And then that handles to the plain old telephone system. You got your phone number, and you're trying to call someone else's phone number, and the phone network handles all that. But the data comes in through your modem, back across the RS-232, and back across your bus, and shows up on your screen. That's one way that you can use RS-232. Or these days, if you want to talk to something else, you can talk to basically anything else that also has RS-232. Use a null modem, basically take out the modem, use a null modem cable, and all they do is they swap these two lines, the flow control lines and the transmit receive, and you can basically talk to another RS-232 system. You know, PS2. I've talked to my modern PCs. This socket, if you don't have a desktop where you can put in an ASCII card or PCI card or whatever, if you have to use a PCI for a laptop. I found the socket brand, they're expensive to find, and they are fast. So I'll talk more about that in a moment. Those are the fastest PCMCIA serial interfaces that I found. I don't know what's in them. I haven't cracked one open to see what chips are in there. So I wanted to go fast. I wanted to go I've seen through RS-232 that you can go faster than 150, 200. You can really crank it up. And I said, I want to go as fast as possible, but I saw these devices and they're like $60. And you can't just buy one, you have to buy two of them because you have to hook them on both ends of the computer. And I said, man, I'm going to cheap out. I don't want to spend $120 for an experiment. So I found this, and you can get it closer for like $10. And it's a thermal, it's for one of those thermal printers for points of sale. And it doesn't really, it says RS-232, but it says it's intended for thermal printer cable, sorry. And since it goes to a printer device, it doesn't spell it out here, but it's a null modem cable. It already is a null modem. It's not, yeah, it's talking directly to another device. And so I kind of gambled on that. I didn't know it was a null modem cable, but I ordered one. I verified it is a null modem cable. They, on their website, when I ordered it, they already had one open showing what chip it is. And so I was reading into that, and I said, what's in this thing? It's got a 48 megahertz clock, and it's got a huge transmit receive buffer, 500 bytes. Like, usually it's like 16 bytes, but this one's 540 transmit, 576 receive buffer. So I said, all right, that sounds interesting. For $10, I'll get a couple of them. And so I hooked them up. This is just showing how other ways you can hook up those USB things if you want to do RS-232. If you need, you can get ginger changers and null modem adapters. Usually they're regular serial cables, and you can get the null modem right in between them. That's one way, but I hooked up these cables. I like Jim, his CBM stuff. Even though it's CBM, his stuff works for anything on the RS-232. It's not really Commodore only. You get these modem 232 devices, hooks it up to Wi-Fi. Yeah, we got a couple more minutes. Jim, who owns and makes these particular Wii modems, he goes to VCF East up in, Midwest, no, Mideast, the one in Chicago. He hangs out up there. He did some firmware updates. He's got it close to 921. It wasn't quite there, but it can do the 460,000 baud rate. This is the last chart I really wanted to show. I was playing with all these different systems, going back to an old IBM PC, the 4.7, and it just doesn't have enough oomph to really, it can do 0.9, that's all it can do in its stock configuration. You have to hook in an upgraded serial card or beef up the megahertz. You can put in maybe a V20 or V30 maybe. But I had a 286, a 386, and all this is showing just kind of, I didn't see a chart like this anywhere. What's the typical baud rate or speed that you should get out of it? Like, is my computer working as it should? And this is what a chart that I'm able to get. That socket on the PCMCIA, yeah, I was getting really good rates. I did achieve 89 bytes a second, kilobytes a second, using Z modem, and I was watching Z modem, and it was reporting that, and that's pretty darn close to the 921 baud rate. So that's showing through RS-232, and that was a Pentium 3 at 600 megahertz. Talking to my modern laptop that it was able to achieve. So I found whatever's in that PCMCIA card, it was able to do it. The USB thing that I was just showing, the cables that it was good. It was only 66.9, so it's not doing the full 921. It's definitely beating 480. But that's using, you know, a high-end computer, a 3 gigahertz to a 3 gigahertz machine, you know, cheating through USB. But it is using RS-232 to do that speed. The other thing I didn't see a chart on is they always say the parallel port is faster. And it's like, is it really? And it is, but it's not like 8 times faster. Maybe 1.5 or 2 times faster. Because the secret there is you can't really use all 8 pins. You can only use like 4 pins on the receive on a standard parallel cable. So it is faster if you do have that available. There's a program, File Maven. All this parallel port, I had to use the older computers, the older 386. The parallel programs, I haven't found one that works under like modern 64-bit Windows. They've kind of abandoned the parallel port.
Yeah, normally you can't bank one that's not on the bus.
Uh-huh.
So if it's on USB, then you don't get that.
Yeah. And I was playing around with the Wii modems. How fast could those get? So this is wireless. The other thing on Jim's version of those Wii modems, it's not Bluetooth, but he somehow connects them. I don't know if it's a direct, I don't know, he'll have to elaborate how he wirelessly connects them through a different protocol. So it's a high speed, as long as you're using 2 of those, I thought it was Bluetooth because it's darn near those speeds. But you put it in this like wireless high speed mode and then it syncs up with the one. I thought it was Bluetooth because it's range limited. It has to be within like the same room, but it is wireless, and it was able to get 13 kilobytes a second using Y modem. Interesting enough, I always thought Z modem was like always faster than Y modem, and that's not actually true. There are cases where Y modem. Jim was telling me there's under Z modem, there's features of it where it kind of needs a synchronization or has to kind of resend the packet if it doesn't have that. And so wireless, your rate is kind of varying all the time. So Y modem actually ends up usually faster if you're in a wireless configuration. All that said, RS-232, right, the slowest USB is orders of magnitude faster than RS-232, and that's still true. When USB first came out, 1.1, its low-speed version, you know, 180 kilobytes a second, approximately, on what you could get out of these. So that's why in the modern day, almost everyone's using USB. It is faster. I will say one advantage of RS-232 is the distance. I don't know if anyone can get 50 feet out of a USB cable. I mean, on its own, you can get amplified and powered USB cables. So RS-232, it's kind of waning, but a lot of people throughout the event have told me they're still using RS-232 on their home computers for mice and other devices. It's the most kind of stable and understood, and it has that legacy going back over 100 years. You know, for whatever reason, if USB fails, you know, there's a lot more that USB can do, and so there's kind of some risk and dangers in using it. You can understand RS-232 easier, in my opinion. So we'll see if its legacy is going to live on for the next 50 years. I think it has a good chance, but I think that's it. Just summarizing RS-232. Thanks. And any other specific questions? They're going to do the video, and I'll probably have some links on like that chart I was showing and how I was doing the setup of the speed. Yeah, that's all I have.
What's the farthest distance you've seen RS-232?
I wanted to do that here at VCF and like run a cable, you know, clear across the buildings. Only really about 30 feet. I haven't really gone that far on regular. I haven't run that long of a cable on RS-232.
I've seen about 100 feet in industrial settings.
And that, do you know what speed, like 9600?
Yeah, it would be
Yeah.
1200.
Yeah.
Punch in the CNC program.
There's one chart I took out was factories. They were still using RS-232. They found it more reliable. And it was saying at 1200 baud. But I imagine that was like way more than 200 feet because they've got some, it was like a pump. I found on eBay, it was a used pump. It was like $500 for this industrial pump, and it supported RS-232. They could get the range out of it a couple hundred feet, but then it said it was only, 1200 baud. You know, they just need a trickle of status of whatever is happening to this pump, if it's overheating or has it jammed up. And so they deemed it more reliable. So
I want to say back in the 90s, I did a doctor's office, or not doctor, the billing, and they were using dump terminals. Cat 5, 9600 baud maybe.
Yeah.
And I think that they were maybe some of those were about 100 feet. Yeah.
Okay. That reminds me of the old libraries growing up before Ethernet was everywhere. Yeah, I remember using dumb terminals in the library, and they were connect, you know, the machine that they had that was doing their actual catalog. Yeah, that was probably at least 100 feet away. Now I don't know what baud rate they were using. I don't know if it was 300 baud or not, but so. All right. Any other questions? Thank you all. Oh, that one.
PBS, you run have a unifying theme, or was it just regional?
I grew up in Florida, so I ran it in Florida in Gainesville at that university. I guess my boast is the peak was like about 50 calls a day. I called it the Lost Cities was the first name, and then I renamed it to the Center of the Universe. There's more to that story. I live next door to a temple area called the Temple of the Universe. And so that influenced, all right, I'll name my BBS the Center of the Universe. And so they're still around there in North Florida. So thanks. All right, thanks.
Thank you.
Thank you.